Hi, everyone. After a hiatus, we're absolutely thrilled to restart the Galaxy SIG with John Woo, who is a scientist at the Space Telescope Science Institute, and Johns Hopkins. And let's see, has been there basically since graduating from Rutgers, if I remember correctly. So it was one move, one stop move. And so John is my go-to person if I talk about machine learning or I don't understand something. He's one of the two people that I then ask like stupid questions of. And he's very patient, so I'm very happy to collaborate with him. And we both share an interest in galaxy morphology, so I'm absolutely thrilled to have John talk today. So, John, do you want to take it away?
Yeah, sure. Let me share my screen. I'm gonna give the warning that there's a bit of drilling and hammering going on outside my office right now. So if anything gets lost, just feel free to, ping me and let me know. You can also move some windows. Hopefully you can see my screen. Yeah. All
Yes,
right.
yes, we can.
Thank you. Well, yes, it's absolutely my privilege to talk to you this morning about interpretable artificial intelligence and machine learning and how it's going to drive scientific discovery, especially in the field of galaxy evolution formation, which is really the area of science that I call home. Um, I guess even before I get started, I want to also say that it's a privilege to be able to talk here and talk about science that has been supported by NASA and also the National Science Foundation, which have been critical for my career and I think advancing a lot of interesting scientific insight. So I don't want to take it for granted that, that this kind of science can be done because of the coordination and effort and support that even taxpayers, are ultimately, driving and enabling for the rest of the world. Okay, so specifically though, today I'm going to talk a little about two different things, and I'm actually going to talk about this pretty casually. I want to be forward thinking. I want to be a little more open-ended, and so I'm not going to just try to highlight like my papers or whatever, but I really want to like lead this into discussion because I understand there's 30 minutes or so after my brief talk that we can continue discussing. And so I want to set the stage on galaxy scaling relations, right? Which is something that survey astronomy has really enabled to blossom and help us understand what typical galaxies look like and what they do as they evolve, right? We've learned this from population level studies, large galaxy surveys. And in particular, I want to focus on the pixel scale because, in galaxy image cutouts, there's a ton of information which has historically been underutilized. Now we have the tools to actually make use of that data. So not only do I want to talk about galaxy scaling relations that bridge on the physics as well as the morphologies, the appearances of galaxies, which will be critical for like Roman, Rubin and Euclid. I also want to talk about the rare anomalies that depart from those scaling laws, right? And those are the kinds of case studies that help us test our understanding of astrophysics, the processes of like the different physics at different scales. And we can follow that up with things like Hubble, with observatories like Hubble and JWST, and eventually HWO, so that we can understand galaxy formation evolution at the extremes. And my take is that artificial intelligence can help drive both of these, right? The population level things and the rare anomalies. And in order to really get the most bang for our buck, interpretability is going to be key. So that's what I want to focus on. Okay, just to zoom back, 100 years, we've known that galaxy appearances correlate strongly with their physical properties, right? And this is because the evolutionary histories of these galaxies are imprinted on their morphologies. And so whenever we talk about galaxies at the pixel scales, I think of galaxy image cutouts kind of like these, where we can see most, if not all, of the galaxy. And, we have our own intuitions about how that galaxy morphology is allowing us to, also get a sense of what kind of physics is going on in the galaxies. I also want to mention, by the way, that galaxy morphology isn't truly a classification problem. There's really a continuum of galaxy types. There are irregulars, things that fall out of like the typical classes we use. And so I really want to stress that like we should be thinking about these kinds of problems, thinking about galaxies as and their morphologies as like points on a scaling relation. There are scaling laws where the mass and the metallicity and the star formation rate and all that of galaxies actually correlates with their appearances. And even though we can't have a single morphological parameter, it is still useful to think about galaxy morphology as a continuum on which we could and we can put that on some sort of scaling law. Okay, but so often, instead of looking at those beautiful pictures at the pixel scale, we reduce galaxies to just a few summary statistics or like photometric parameters, right? It's useful to use with catalogs of galaxy data, and especially when we're in like the data science domain, right? The data-rich domain where we have hundreds of millions of galaxies that we're entering in. When Roman, wide area, highlight to wide area surveys are going to come up, it's going to be really tempting to reduce those beautiful galaxies to just a few columns. And here are 9 galaxies that I've grabbed from the DESI legacy imaging surveys. They've got basically the same R band magnitude and G minus R colors. So the question then is, what can we say about their physical properties? Very little from just this, right? But obviously, if you get these are the same galaxies, but we grab the image cutouts, we can see a lot more information here. We can say something about their evolutionary pathways, their star formation histories. And as when I, introduced this topic, like we finally have the tools to exploit that pixel level information. Those tools come in the form of deep neural networks. And specifically for images, we think of convolutional neural networks. These are basically the ideas that is really that you can do matched filtering. You look for particular filters or particular morphological features, and you just try to match them over your image. And if you do that sequentially, you can formulate, sort of more abstract or sort of higher level features that describe the kinds of morphologies that should be seen in your image cutouts in your population of galaxies. And so in some sense, this CNN, which I'm denoting as like this sort of cascade of colored rectangles here, is an operator that turns your input image, a galaxy, array of pixels, into a list of features where, the height of this sort of bar chart looking thing is like the feature strength. Okay, and the idea is that you can say, here are the different features that exist in my image, things like how tightly wound spiral arms are, or maybe does this have like a off-center H2 region, or blah, blah, blah. Those are the kinds of features that we learn using a CNN, something that learns directly from the data, extracts from the image, and then finally can be used to make predictions. And this has been really successful. I really built my career on this, the idea that, galaxy images can lead to physical insights. And our interpretation really is that this means that, in some sense, the morphologies of the galaxies live on some kind of a galaxy scaling law. And I mean that like more than just like the morphological dimensions that we typically think about, things like, luminosity size relationship, or even like a morphology environmental density relation. CNNs kind of give us, like a lot of parameters, right? All these different features at the end of, that become extracted out of the images and can be used somehow to derive things like the gas phase metallicity of images, which we can do extremely well enough to reconstruct the mass metallicity relation at redshift 0 with 0 additional scatter, right? We can estimate the H1 or the gas mass fractions of galaxies as well, extremely accurately. And in fact, we can even start to attribute the pixels in those image cutouts that lead to either high or low gas mass predictions. And these are things that like astronomers knew about, right? Like if you asked an experienced astronomer, like, hey, does this look like a gas-rich galaxy? Like if they've looked at thousands of galaxies before, they can instantly, they could probably guess the gas mass fraction or whatever pretty accurately. And this to me tells us that like we knew all along that there's something about the morphologies that like allow them to live on these galaxy scaling laws. We just were never able to write that down because it's very complicated, or like there's no simple heuristic. And in fact, there's even another example, which I actually partnered with Bene to do, and it was just a huge privilege to see that not only can you use, galaxy image cutouts to estimate metallicity or gas mass, but also you can estimate almost the entire optical spectrum. And we were able to show that this works not only in the training data set, but also, in this example for Rubin's galaxy or UGC 2885, that you can really push this kind of analysis, pretty far. And the fact that we were able to successfully verify, the spectrum of this particular galaxy, which has a low luminosity AGN, and validate that, it shows that the scaling laws that we think that these galaxies live on actually extend to that extreme mass range for this particularly large and massive galaxy.
John, I have a
Yeah,
question.
yeah, sure.
What you're showing there right now, where you have H1 poor and H1 rich, if I look at that closely, all the dots sort of match up. Aren't they the same galaxy with some sort of different stretch or different band?
Oh, yeah. So, okay, right. So maybe I should say more about this example. So this comes from a paper I wrote in 2020. And this particular example is showing the same galaxy. We're asking counterfactuals. This turns out to be an H1 rich galaxy. It's actually got like kind of like a merging or interacting like component. And there's sort of a redder central, galaxy with actually like a bit of a bar. And then there's like sort of this H1 region and some interactions. And I think there's another galaxy over to the north. Now, the interesting part about this is that this is an H1 rich galaxy. And we can say which pixels contributed to the correct convolutional neural network prediction that this was an H1 rich source. But we can also ask a counterfactual, and this is where interpretability starts to come in. You can actually say, but hey, what are the pixels that would have led to you believing this is a low or gas poor galaxy? And in fact, it can also do that as well. So that's the reason why it is the same galaxy.
Oh, thank you. I thought I was going crazy there for a moment.
Oh yeah, yeah. Sorry. Yeah, no, that's right. You could see through the opacity here. Anyway, so all this is to say, right? Like, these galaxy scaling laws tell us a lot about how their different physical properties are connected. And I think this is a huge success in like terms of what we've been able to do with data-driven astronomy. Again, I built my career on this, so I'm very invested. I think this is really interesting to study, just in terms of learning more about different galaxies and the connection modes between them, between their physical properties. So I told you a story though. I'm gonna take a sip of water. I told you the story that like we take a galaxy image and we reduce it to a bunch of, features. And in fact, we can even say these features have meanings like, this is how point source like, this galaxy is, or how asymmetric it is, or things like that. But the truth is, those features are not so interpretable. They actually end up being a total mess because what happens is the different, basically you have, 1,000 features extracted from an image. And those 1,000 features might represent some weird combination of 1,000 semantic meanings, that is, actual like morphological features that you and I might interpret out of them, but they're smeared or distributed across all these different neurons in the neural network. And so that is to say, it's not a one-to-one mapping in the sense that like I can read the strength of this one feature as, oh, this is how tight winding spiral arms, how much does this galaxy have a tight winding spiral arms? But rather, like the semantic feature of tight winding spiral arms might be distributed across, a dozen different neurons. And in fact, each neuron might contain little bits of lots of different semantic features. And this has been seen and this has been known in other applications of convolutional neural networks. If you look at something trained on like terrestrial images, which can which can find cats and dogs and boats and cars and stuff like that, there's one neuron, for example, that activates, or basically it fires anytime you put in an image of a cat or the front of a car, or apparently cat faces, cat legs, and the fronts of cars. And this is like what this, I think this paper they called it polysemanticity. That is that semantic, and poly meaning many semantics or many meanings per neuron. And so this is kind of like a mess because this means that you really don't actually know what your neural network is learning or how it's representing the data. So because we, are grounded in trying to understand the physics of what's going on, I think it is actually important to peer into the neural network and better understand what are the features that arise from a trained CNN. And in fact, we can do this two ways. I'm going to talk about these. And bear with me, this might get a little bit technical, but I'll just try to cover the high level picture, right? So I said we have a data set. So we've got, many different images of galaxies. We can feed these into a CNN and that extracts a bunch of features from them. We can then train another neural network. So after we're done learning from the CNN, we can grab this list of features and we can try to reconstruct it, but force it to go through what we call a bottleneck layer, or basically a small latent space. This is kind of similar to like how you might think of like principal components analysis works. If this is just a projection matrix, you take a projection matrix, you project it down onto a low dimensional space, and you deproject it back onto a high dimensional space. You've got a low-dimensional representation of your high-dimensional features. But that's not guaranteed to actually disentangle the meanings of the different features. And if you've ever actually done this in practice with PCA or any simplified linear method, you end up with uninterpretable features again, just a smaller number of them. So that's not particularly helpful. What an autoencoder does, is this is now a linear or non-linear version of PCA in some sense, is you put a neural network here and a neural network there. One is called an encoder and one is called a decoder. And it encodes that features into some low-dimensional space. And critically, the way that we represent it is that we actually enforce a sparsity constraint on the latent space, basically on this middle layer here. So these features that we've extracted from the images, from Galaxy images, are then mapped onto, just a small number of features. Here, I'm just showing 4 features. And this sparsity constraint encourages what this is called a sparse autoencoder, or an SAE. It encourages, the representations to be unified if they're semantically similar, because you don't want to have redundant features. Otherwise, you waste one of your precious neurons that's allowed to be activated. But otherwise, you try to describe the image in as few features as possible. So, to summarize, like this sparse autoencoder, the sparsity constraint encourages the autoencoder to disentangle those CNN learned features into something that is more interpretable. That's the hope. And this is actually based out of work that we did last summer. So I work with 2 brilliant undergrads, Charlie O'Neill and Christine Ye, and also Kartik Iyer, who is brilliant in all sorts of other ways too. But we worked on text data, so crunching archive papers and processed them with these kinds of sparse autoencoders where we extracted the semantic meanings. And we basically were able to interpret the topics in an unsupervised fashion and find the keywords and the different types of themes and stuff that existed in the astronomical literature. And so there's a lot of interesting work we've done here with the sparse autoencoders. And this, all in all, has actually been very popular in the AI safety and alignment community. The reason is that they do believe that this adds a layer of interpretability over these features. And in fact, those features it's really helpful because you can look into these features and see, oh, do these features correspond to something I don't want, say, a large language model? I don't want ChatGPT to respond in a toxic attitude, or I don't want it to, discuss something, that it shouldn't be like going off the rails and telling you how to make weapons or something like that. Those are actually features that can be found and steered. You can intervene on them within these sparse autoencoders. So this has been a subject of intense research from the AI community. And let me just say a little more about this in practice. Actually, I'm going to gloss over the details because I want to save some time for more discussion. But this is kind of to reiterate, we take our extracted features from the CNN, we basically pass it through this very simple neural network where it is basically encoded into what we call an over-complete basis. Basically, there's this latent space, which actually has a larger dimensionality than the input dimension of the features. But then we impose a sparsity constraint where we say, okay, now everything that's not, only the top 4 features or top K features are allowed to remain. Everything else goes down to 0. We just throw those away. And so that's what I mean by the sparsity constraint. We then have a linear layer, which is to say basically a deprojection matrix into this reconstruction. And we optimize this neural network now by trying to make the input and the reconstruction as close to each other as possible. All right, so that's how it works in practice. Why does this matter? Well, here are some example image cutouts from the DESI Legacy Imaging Survey, which also have spectra from the DR1 release. And this is a very preliminary example. There's no paper associated with this, but I think this is a very interesting line of research. So I thought that these galaxies got separate features for some reason, according to a sparse autoencoder trained over, a CNN. And I thought that these looked quite similar. Like, to me, I was like, okay, these kind of like, elliptical-esque galaxies, they're obviously quite red. And I'm showing, 2 different features. So why are these semantically different? It turns out that this top population, which is shown in okay, so the top population here tends to be dusty star-forming galaxies, and the lower population are like lower in dust, lower AV, and have older stellar populations. And I'm showing this in sort of this bivariate distribution plot here, which, plots the same ones. The blue ones are the dusty star-forming galaxies. So for that population of systems, if you derive the log ages, they tend to be a little bit younger, and they tend to have, this is the histogram showing the AV, they tend to be dustier as well, or they have more attenuation. And then for this lower panel, we're seeing galaxies which sort of by eye to me seem like they should be similar to the top one, but they actually tend to have older ages, and they tend to have a lot less dust. So there's something about these, this sparse autoencoder, which is trained on a neural network, which I didn't train, I just grabbed, I trained this sparse autoencoder to interpret the features. We're able to break the age dust degeneracy in a way that, that hopefully is semantically meaningful. Obviously, it's meaningful because we can now look at how these physical properties, right, correlate with their observed morphologies. And there's something in here which is telling us that, in fact, the age dust degeneracy is being broken. So this is very early work. I'm super excited about this kind of stuff, and I'd love to chat more about it if this is the kind of thing you're interested in. This is an application of SAEs, which allow us to really leverage the power at the pixel scale. Another example, which, again, just like very quick off the bat, I saw that Euclid, recently had their quick data release as well. And there was a neural network that was trained, on that. So we have CNN extracted features from the Galaxies SIG collaboration. This is called ZooBot. And you can actually take, and not the literal classifications that this CNN is making, but rather you can take the layer before it and try to understand, hey, can I actually go and find semantically meaningful features out of this, essentially, this mostly like, pre-trained neural network, which knows about Euclid imaging, but doesn't actually know about literally like how the, classification should be made. It's not trying to classify like, is this a three-arm spiral or a whatever? And it turns out that, from that intermediate layer, you can actually extract semantically meaningful information too. And this is like, I talked to Mike Walmsley about this, and he was actually pretty stunned that this was possible. He's the one who trained ZooBot. It turns out that by training an SAE, you can actually grab, you can see like these are just 6 different classes of features that seem to be individual activations. So different neurons. One neuron fires on, these kind of smooth galaxies, ellipticals. One of them actually fires on ellipticals that actually, if you have good vision, you can see that all of these have little blue satellites or little smudges next to them. That's a separate distinct feature. This is one which is like blue galaxies that seem to have a little bit like a hint of like a ring structure around a lot of them. Some of them are actual ring galaxies. And a lot of them also have a linear, like sort of filamentary looking thing. I don't know why that is a structure. Again, these are things that are falling right out of the data. You can see some nice spirals, barred spirals in here. You can see some edge on disk galaxies. And in fact, you can even see some, artifacts that are due to internal reflection, within the camera. So again, not work that is published or anything, but very interesting work that, we can continue to pursue. I said that there are 2 different ways that we can think about, using neural networks with interpretability baked in. And this one is actually even more direct. This is the second one I want to cover, which is to say that you can intrinsically train a neural network to have sparse representations. So rather than post hoc, after having a neural network, grabbing the weights from somewhere and using it as just a feature extractor and then interpreting those features, what I'm saying now is we can actually feed in a neural network, and while training, we impose a sparsity constraint such that it can make predictions or do some task we want of it. But then when we're training the neural network, we impose that sparsity constraint. And so that bakes into the neural network. And that changes the internal representations. We're making the CNN interpretable by design. And this actually is a paper that I've published. So this is a work that I wrote earlier this year. You can find it in AppJ, and I'm calling this like a sparse feature network. It's literally what it's doing. It's trying to find a sparse representation, a sparse basis on which images can be described. Okay. Let me just show an application here. So in this case, we're grabbing image cutouts from Sloan, and we're trying to predict just the line fluxes for H alpha, H beta, O3, and N2. Those 4 lines, as you probably know, are used to distinguish star-forming galaxies from AGN using the popular BPT diagram. There's sort of a dividing line, but in general, lower ionization, low excitation gas is indicative of things that are coming from star forming sources, and up here, higher excitation AGN, there's, you know, there's AGN, I mean, there's Seyfarth's, there's liars or liners, whatever you want to say. But, we're going to go with just a binary classification to make this easier. In fact, actually, we're not going to use the classification directly. We're just going to try to predict these line fluxes using a sparse feature network. All right, so that's the problem setup. Now, if we train the neural network, this is what we find falls out from the CNN. We can train the neural network to predict those line fluxes, and then we can look at the actual true line fluxes, and highlighting the galaxies which most strongly activate the kinds of features that are learned somehow by the galaxy. So this is now looking at like a particular feature. This is the first feature that I want to cover, something that reveals low mass and metallicity and high star formation. So relatively young dwarf-looking galaxies. And the examples that you see on the right are literally just the top 9 examples. And the brighter points within this BPT diagram here show the examples where they most strongly activate. And so what we see is these are like objects that have very low N2, which is indeed a metallicity indicator. And in fact, what we find is that, yeah, these look like dwarf galaxies that are, forming, have a relatively high specific star formation rate. And, this is not something that was guaranteed to fall out of the data, but the data was able to segment and say, like, this is an important population of galaxies, and I'm going to, reserve one of my precious few neurons of my sparse neurons to allocate to this. Another feature, a second feature, is actually something that seems to activate mostly on the opposite, which is high N2, and galaxies which actually do kind of fall in that liner/liar camp. Not super high ionization per se, but objects that have older stellar populations and high metallicity. And so these, by eye, you can clearly see that these are galaxies that might be like brightest group or cluster galaxies, and they are galaxies. If you look at their position in the BPT diagram, they seem to be on the liner side. A third feature that I'm really excited about is something that seems to reveal high gas excitation and mergers. So these extreme emission line galaxies. By eye, you can immediately see that these are very interesting starbursting galaxies, very compact, and they contain a lot of emission line or like high emission lines, high O3 relative to H beta, and something that hovers very close to this dividing line between star-forming galaxies. Historically, these are galaxies that actually tend to be found in, like an indicative or seem to be analogous to high redshift galaxies, right? Where you have sort of a high pressure disk or local, high density gas disk, and have very, very high excitation. And these are very interesting too to me because I think that they resemble Lyman continuum leaker candidates. And they also seem to be galaxies that are sort of in this like Lyman break galaxy analog range. So these are very interesting for follow-up. It's another population that I think is worth considering, like looking into further, because I think there's something about the fact that this sparse feature network was able to find it from this population, and decide to hone in on it, that this ends up being something that's physically relevant. Again, connecting the morphology with the physical conditions in the galaxy. And then finally, or at least the fourth feature that I want to focus on ends up being something that seems to be kind of diffuse. They often tend to be face-on sort of star-forming, but lower surface brightness galaxies. And these tend to be sort of lower in general in the ionization, but sort of safely in the star-forming locus. Okay, so that's just like an atlas of 4 features. There are more features that are found here, by the way, but these are the ones that are frequently activated, which is why I wanted to show them. But a cool thing that you can do actually is that you can write down the O3 over H beta ratio, or even like the gas metallicity, as a linear combination of the activation strengths of each feature that is extracted. And so this is very powerful because it tells you almost like a very simple way to say, how do I actually derive these kinds of things, right? How do I derive the gas phase metallicity? These features, this is actually a separately trained CNN, which is why I'm showing a different example of this. But this image cutout in this case represents the activation strength of that particular feature. And it's just a linear combination of these two things. And you can actually see, you can read from the coefficients and you can look at what those features actually entail as a way to interpret the physics of what exactly is going on. Like what is it that, low metallicity or low N2 over AH alpha seems to give you in terms of this kind of physical interpretation. And another specific example, again, really early days, is this example where we're looking for delta SFR over the star forming sequence of galaxies, SFR against M star. And in different bins of stellar mass, we can actually look for the galaxies that activate most strongly on that particular this set of features. And what we find, interestingly enough, is that there are actually a lot of these galaxies that have this sort of like purpley stuff. This is high equivalent with H alpha and also high nebular continuum sources, something which obviously is present in the images, but is very hard to measure until you have a spectrum. But what I would argue is that you can literally see the high nebular continuum sources from the imaging. And maybe you can come up with a heuristic or a handcrafted feature that can extract that for you through a standard photometric pipeline. But CNNs seem to basically just find this for free just because they're looking for things that are extreme starbursts. And so this is, again, another promise of using these sparse feature networks and baking in interpretability directly into your neural network system. So let me just leave up the summary here. I'm not going to sort of remind you of what I just said. I think that this is a really promising approach. And I think there are multiple ways that you can get at interpretability in machine learning for astrophysics. I'm super excited for what Rubin is going to bring, what Euclid is already bringing to the table, and the potential for follow-up with, the current, NASA telescopes and upcoming missions, which are going to, push, especially like UV science, all that stuff even further. So thanks for your time. Happy to move into discussion. Whatever.
That's excellent. Thank you so much. I have a question, of course, but I'll open it up to the room first before I jump in. And anybody want to jump in, or just raise a hand? Somebody stop me, I think, to quote the mask. All right, I have a question. With the encoder decoder component, it almost feels like if you have some sort of combination of weights that you came out of your CNN. So you could, for example, use Google's photo classifier or what have you. Like you could almost use um, it doesn't quite, like you've turned your images somehow magically into a list of numbers, right? So it almost doesn't matter what that first CNN is, as long as you have an autoencoder that can then sort of weed everything down to its basic components, and then you can reinterpret it and say like, okay, this is the things that I'm measuring, or this is the classifications that you're getting out. So you know that I like morphometrics, right? We've been trying to come up with features sort of before we had CNNs using concentration, asymmetry, smoothness. There's a fairly long list, but it's always been a little fuzzy of how useful any of them are, or how useful. I think we're at a dozen at this point. So it feels like I have a feature space that is sort of that I'm familiar with, at least, or at least I've blundered around in. And then can I use an autoencoder on that, for example? Would that be a
Yeah, right. I mean, so that is one way to test a couple of things. You can see, you can use an autoencoder to understand, well, actually, how redundant are these features with each other? Because if you can sort of reconstruct them with high fidelity with just like, instead of 12, you only have like 4. I don't think that's possible. But, like if that's the case, then that would tell you something important about, whether or not you really needed all 12. Another thing that you could think about is like, well, if you use an autoencoder, how well do those learned sort of representations correlate with the actual things that you think are important for galaxy evolution, right? Like if none of them can tell you anything about the star formation properties of the galaxy, again, I don't think that's likely, but if none of them can tell you that, then you're missing information. And I think that like this ends up being an interesting experiment, as you say, like to understand like what's the information content. You can do this formally with mutual information statistics and things like that. But ultimately you want to understand like, yeah, what is the information content in here? And to me, what's interesting is, are we able to describe something that, hasn't been probed before? We thought we didn't know how to extract extreme emission line galaxies, maybe, without spectroscopy or without far UV or something, but maybe you can just directly from optical imaging cutouts. And I think that that's actually like where I think the most opportunity for gain is. And maybe you can describe that in existing, existing morphometrics. So that's also another line of research.
Swara has a question. Swara?
Okay, can you hear me?
Yes.
Yeah.
Okay. I have a couple of questions, but and I also joined a little late because I came from another meeting. My first question was about the BPT diagrams. They look very impressive. I'm pretty impressed with this talk, but want to follow a little more. What were the actual inputs for? Yes, yeah, you can stay on the low mass metallicity. Yeah. So what were the actual inputs for this one?
Yeah, so all we input were like these, literally these images.
Okay.
So we had, I don't know, 200,000 or something of these images, which, were galaxies for which we knew that, from MPHHU, spectroscopy, or whatever, they're a part of the main galaxy sample. So we knew that we could derive O3, line flux, H beta line flux, H alpha line flux, and N2 line flux. And then we trained them to simply predict those line strengths and nothing else. And on the basis of that, the neural network came up with the internal organization or representation of them where it decided that this was a very important feature, such that, the stronger this feature was, things that would find these particular types of galaxies, galaxies that look like these, they would end up being more on sort of the low N2, low metallicity side of the BPT diagram, I guess. Is that helpful?
Yeah. Okay. So all you're really giving is the images that have been trained on. So you have a set of galaxies for which you have the spectra and the morphologies, and you're also feeding in the color information. Is that correct?
We're literally just giving it a 3 by 100 by 100 pixel array. That's it. Like, so it's just an array of numbers. Each galaxy is represented only as like the GRI band image cutouts and nothing else.
Okay.
And then from that, it is trained to infer these line fluxes. It probably needs to extract something like colors and color gradients and
Yeah.
sizes and something about that, right? But this is exactly the point. Is like, what exactly are we learning? And it turns out that the summarized way that it condenses all that information is it says, okay, well, here's one mode of interesting types of features, and here's another mode that galaxies can, be low or high on, and here's a third mode, which involves mergers and, extreme nebular emission, and here's a fourth one. And in fact, galaxies are combinations of these. So in fact, many of them they actually activate all of these or three or two of these four features at the same time, and that's okay because you can just have a linear combination of the strengths of these features, which ultimately tell you something like how much O3 do I expect from this galaxy. It's kind of like saying, okay, I can have a bulge and a disk, and I can have, I don't know, a tidal, stream or something, and all that information tells me something, but I can combine them. All right.
Okay. And the points are, so each of the individual points there are are they actually points? Each point there represents one galaxy, or are they kind of star-forming
Yep.
pixels?
So each is a galaxy. Yep. So this is a galaxy with this particular combination of N2 over H alpha
Okay.
and H beta. Yep.
Interesting. So,
And the coloring of
okay,
the
so
point is
the measurement you're getting for the line ratio is actually the integrated information.
yes. It's integrated
Okay.
over the whatever 1.5 or 3 arc second Sloan
Okay.
fiber.
Okay, so you have color information and morphology as the input, or the entire cutout in the sense of both size and morphology.
Mhm.
And you get the flux ratio. Okay. All right.
Yeah. Happy to chat more offline. But
Yeah, I was also wondering if you have it would be kind of nice to see a plot that shows, you use a certain set for training, and then you keep another set as a sample that you can use for testing, right?
that's right.
Where you don't use it for training, but then so that the accuracy of
Oh, that's right. Yeah. So I only show the examples that were not trained. So these were all never seen before.
Right.
Uh, so this is like 20% of the sample. There's another, so this is like 80,000 galaxies, but there's another like 200,000 or whatever. There's like 50,000 galaxies. Yeah, there's another 200,000 that are like that
Yeah.
have been trained, but I'm not
So what
showing.
I was saying is if you have another set where, you don't use it for training, but you have both spectroscopy and then you can actually check whether the line ratios that you're getting uh, compared to what you would get with spectroscopy, right? I mean, whether they
Yeah,
match.
yeah, that's right. Yeah. Yeah, so
Would
what
have
that
been
would
nice to see that.
that's right. It basically looks like this, but it's cleaner. So
Yeah.
it's how do I put it? The predictions would be cleaner because actually those trends end up being a more like obviously linear gradient because that's the neural network predictions and the neural network representations. So it ends up actually kind of like really falling on this line. The
Mm-hmm.
reason I wanted to show the validation set using the ground truths rather than the predictions is because there is some error, as you state correctly. Like, it's not perfectly recovering these lines or line fluxes or ratios, but what it does is that adds some natural scatter back to it. So you can see that's why some things, kind of scatter over the line and things like that. But actually, the version of this, and I think I do have it somewhere where you use the predictive values. It's a kind of a cleaner, like a very like more simple gradient. Um, because that's both the coloring and the locus of the points are coming in that case from the neural network, from the same source.
Okay, thank you. I'll let others ask questions.
Yeah, yeah. And thanks for the questions.
Yuan, and then Alexandra.
Oh yeah. Hi, John. This is a really, really interesting talk. Thank you so much. And I quickly looked at your paper. You have all the codes on GitHub publicly available, right?
Yeah, yeah.
UMass Amherst, I think definitely at least one of the students here would be really interested in trying your package.
Yeah.
So I have some really basic questions. I think you mentioned that sometimes, you do this really cool machine learning and then you ask the really well-trained observers and they can already see it. I'm just curious if you've tested this on like well-trained, really experienced observers and you just give them some images and ask them to guess where these galaxies would sit on the BPT diagram just for
Hmm.
fun. Mm. And I'm
That's
just kind of
interesting.
curious.
Yeah, I guess that would be a fascinating, like, not citizen science. I mean, it could also
Yeah.
be a citizen science project, but like, no, but like, yeah, right. Just a general thing. Yeah, my intuitions are honed though from like, when I like, for example, when I was one opportunity is when I collaborated with the Saga team, we were
Mm,
trying to find low redshift, very, very low redshift galaxies.
mm,
And we're trying to distinguish them from really, from distant interlopers. And there was, like
mm,
a 100 or even 1,000 fold more background galaxies than like extremely low redshift sources. But I was interested in those really low redshift sources. And like, I talked to these experts who had been conducting the survey for over a decade and
mm,
they had seen, like hundreds of thousands of targets, for which they needed to allocate a spectroscopic fiber. So this was a valuable, decision that they had to make, and they were very well trained because they knew, like they internally could say, oh, this is a low redshift, galaxy because I can tell based on the morphology, I can tell, based on my expected sort of where it falls on the mass metallicity, it's like low metallicity, it's blah blah blah, like the surface brightness, all those kinds of things that they're extrapolating and they're saying like from all that I know that this can't be a high redshift galaxy, it's too compact or whatever. And I think like those are the kinds of intuitions that like yeah experts do have, and like I don't think anybody would be particularly surprised to say that this is probably not a low metallicity galaxy, on this panel, and this is probably not a super super high mass galaxy. But yeah, then the question is like, can they really drop it exactly where you think it should belong in the
yeah,
BPT?
yeah. What's their accuracy compared
That would
with
be
machine?
fascinating. I have no idea about that. Yeah.
Yeah. And then another quick question is, how do you expect the community to use this? Like, I'm not
Mhm.
an observer, but I'm guessing if anybody wants to like identify agents to do follow-up work, I guess they can even skip the spectroscopic survey and just use morphology. Would that like save a lot of resources in a way? I guess
Yeah.
I'm asking because yeah, I'm sure you thought about it, but like tell us
Right.
what we can do with this awesome thing.
I think like my main point here is that like there's actually a lot of information gain that you have by enforcing the sparsity constraint,
Mm,
because it really does make things more interpretable. And what it can let us do, in my opinion, like one of the big things I like out of this is that you can start to come up with selections that don't rely on, tons of expensive follow-up. You can immediately say like, hey, what if like have we been able to get UV follow-up of some of these sources, right? Can we measure the Lyman continuum like leakage? Can we do other types of stuff? Like, are some of these dual AGN, or
mm,
like are some of these, can we infer the nanograv background, on assumed binary black holes, based on the merger rates inferred by this kind of thing. There's a huge wealth of
mm,
possible science that can be done. But the interesting thing is that we've so often just restricted ourselves to the case where we say, oh, this isn't in my photometric catalog. So all I can work with is this stuff,
mm.
right? Or
Yeah.
maybe like a Petrosian radius. But no, we have so much more at our disposal, and I think we should really leverage that.
Cool. Thank you. Thank you so much.
Yep, thank you.
Alessandra?
Yeah, thank you so much for the excellent talk. It was really, really interesting. And so I have a question because I am in the high redshift analog community. And you mentioned Lyman continuum leakage and things like that. Just out of curiosity, how dependent on the image quality and the particular imaging you train on are the predictions? And so, for example, if you get a prediction of, let's say, escape fraction or O32, a predictor that correlates with the escape fraction, could you possibly um, infer that at high redshift from low redshift imaging, for example?
Uh, Yeah, no, so th these are great questions. Yeah, so the in general, things that are trained at low redshift will not generalize to higher redshift. I mean, so in fact, in general, things trained on one data set will not generalize to things that are like extrapolations of that data set, right? So if I trained it on a simulation, a hydrodynamic simulation, even with excellent, ray tracing and dust radiative transfer and all that, but it's not exactly the physics that the real universe obeys, and so in fact, it will fail in very unexpected ways, right? This is the curse of neural networks because they have 10 million parameters or something, so it's not obvious how to say why did this not go right. But this is something known as domain shift. Many folks work on this, including some experts at Fermilab, and I think like that's a pressing question. What I would urge is to to be very careful with the types of data sets that you use. And there are use cases like where if you have a parameter space that you have very valuable opportunities for follow-up, for example, to find Lyman continuum leakers, and you're saying, well, I want to really only just put my, HWO targets, on just a few of the highest quality candidates, for follow-up, I can confirm them that way, right? Or maybe I can even confirm them and say, this fraction of them seems to be bona fide Lyman continuum leakers, but I have some impurity, some contamination fraction. And then you use those statistics propagated to your data set and say, I measured, how inaccurate I am. Let me now say something about the global, the population level statistics of the universe, right? You can sort of you can make corrections for that. So I think there are opportunities here, but you're absolutely right. You have to be very careful here. You definitely can't just take something trained at redshift 0 and propagate it to redshift 6. You also have, of course, different types of image quality, like you say, it matters how many resolution elements you have over your galaxy. I mean, with the decals imaging, I mean, that's a ground-based telescope. If we got images of this with Euclid, it would be really much nicer. And you can see that, when you start to get close to the PSF, you're not going to really get anything more than you can extract from forced photometry, because, like by definition, the PSF, is if that's all you have, then that's all you can work with. And so CNNs become useless then. Yeah. But
I
thanks
see.
for the
Thank
question.
you.
Yeah.
I'm going by the order that they're at the top here. Victor Liu.
Yeah. I just wanted to say that this is a great talk. It's really fascinating. I'm actually interested in this slide that you stopped on right here, which caught my eye. So I'm not very familiar with the uh dust age degeneracy. So I'm actually kind of curious how the network is able to distinguish between these sort of two categories. It seems to me that it's is there something that like it's finding within these images that can let you determine whether one is dusty and star forming versus old solar populations and low dust, essentially?
Yeah, yeah. No, that's a great question. And it's one that I don't have a satisfying answer to yet. But in terms of let me just say two things. One, thanks for reminding me. I probably should have said more about the dust age degeneracy. But the idea is that you can have two underlying galaxy spectra. One is like that of a star-forming galaxy that might be more dusty, and it appears to have, sort of preferential reddening in the bluer bands, right? If you take photometry of it, it looks like, it's something is causing the blue light to drop out, and that might be due to dust. An alternative explanation is that it seems to have not a lot of blue light, but it's not because it's been attenuated by dust, yet remains a star-forming galaxy, but rather it's a galaxy that just intrinsically has old stellar population. All those young stars have gone away. And so it doesn't necessarily have to have a lot of dust. It just never had a lot of blue light. And so this is kind of an annoying, thing that makes it's a degeneracy for spectral energy distribution fitting. And morphology is thought to play a role here, right? Because you should be able to like see something about the dust. Again, these are relatively higher in redshift, so they're kind of farther away. We don't have a lot of resolution elements across the images. I surmise that there's something about the brightness profiles that are seen here that is useful. Information about like the distribution of other sources nearby, which is kind of complicated, right? And it's not obvious. There's too few examples to really say a lot here. Like maybe there are, either more mergers or whatever. Something about like potentially the ellipticities also of these sources, which can tell you that maybe some of them actually have, I don't know, are S zeros or something or other. It's very unclear to me exactly what's being learned here because again, I haven't given this a ton of thought, but I think, in fact, I think that that's actually like that would be a very exciting finding to understand what it is that's actually breaking that degeneracy. And if we can reduce that down to just a single thing, which we do understand, and I think this is the keys to making it understandable, then we should just we should just extract that parameter instead, inspired by this, and then simply say we know how to break the dust stage degeneracy from imaging, and this is going to be a huge benefit for all SED fitting.
Yeah, thank you. Yeah, no, it's actually super fascinating. I feel like images, I guess I haven't really thought of the ellipticity and other factors like that. So that's very illuminating.
Sure, yeah, and maybe you can think of more because yeah, I by no means have a very clear picture here. Thanks.
Allison? Oh, did you just drop out?
Allison, I think you're muted still.
Sorry. Thank you for such a nice talk. I've been aware of some of your work for a while, and it was really nice to get this overview. I'm primarily a spectroscopist, and so thinking about this is really useful since there are going to be so many large imaging data sets. But I find that when I see some of the things that you're talking about, it's things that we've known about for a while, I think. And so when you talk about reconstructing the mass metallicity relation, and you talk about looking at small blue galaxies and thinking that they're low metallicity, or knowing that they're low metallicity, and sort of larger red galaxies, this is not. Are we measuring metallicity, or are we measuring some correlation with something that's related to both metallicity and the appearance, right? Like age. And so I'm curious about how this method can tell us about those underlying correlations, because that's, for example, why strong line diagnostics work. That's why the BPT has the locus that it does, is that there are many sort of correlations that are working together. And I'm wondering if I want to know how to use this kind of tool to investigate that.
Yeah, no, thanks for that question. I mean, I think there's let me just say that like, the way that I present this is often twofold in that before I get to anything that seems like it could be new, we also have to establish trust and validate this. And so that's why, the idea that we can reconstruct mass metallicity and we can do other things that we know is comforting, but maybe not so new, right? But what I think there is an element of like, novelty, or at least really physics, interesting physics, is when we say, like just as with the mass metallicity relation, somebody said, hey, I actually can reduce the variance by including this, either star formation rate or, gas fraction or something, right? Like the idea that there's maybe a fundamental metallicity relation or something, right? Who knows how constant it is with redshift, et cetera. There's discussion around that, but the idea though is that maybe there are other parameters that actually tell us that what we're seeing is a projection of a scaling relation that's in many more dimensions, and we've projected along 2 dimensions. But this is telling us, hey, there's a third dimension that we might want to pay heed to. And I think like morphology has long been in the shadows where it's like, well, what am I supposed to do? There's 100,000 pixels, right? Like that's not a dimension that I want to look at. And I think, with the sparsity constraint, we can actually reduce that to a manageable number of dimensions where we're actually saying like, well, but what if we just only work with a couple of these and we know that they're physically correlated with things? And why don't we see, like, does this contribute something to the intrinsic dimensionality of how to describe all of these galaxies in some high dimensional scaling law? Like, ultimately, I want us to be able to say, like, galaxy from evolution is, for the most part, a 6-dimensional manifold in these.
You want to know what the fundamental parameters.
Exactly, yeah. And
Yeah.
I think that's the way to go.
I guess a related question that kind of builds on something that Swara asked is how well does something like this help you actually understand the intrinsic scatter in some property, right? So there's a lot of interest, for example, in understanding the scatter in the mass metallicity relation. But if you're using a diagnostic that is actually dependent on more than just metallicity, like strong line diagnostics, you get a lower scatter than if you use, for example, direct method, right? So we're already kind of seeing that the strong line diagnostics are kind of a projection of some higher dimensional surface. So can we learn about the intrinsic scatter using methods like this?
Yeah, that's a great point. I don't think we can improve upon something that we're building on top of the assumptions made by, say, strong line diagnostics.
Okay.
To use those. There's a secondary possibility of saying, well, maybe we can compile a sample of things with more, whatever direct temperature methods or something, and actually get a better metallicity indicator. And perhaps there's something to be learned there, but you're still, you're still beholden to the assumptions being made. So I think it's a very important caveat. But at the same time, I do think it tells you something about if you do reduce the variance modulo those assumptions, then there is something, again, there could be a physical correlation at play there, and it's worth investigating. Yep.
Thanks.
Ali?
Hello, can you guys hear me?
Hey, yep.
Good. Hey, John, this was a really great talk. I really liked it. First, I want to confirm is you're basically doing this assuming just GRI and morphology, correct? Those are the 3 main filters I heard.
Yeah, GRI, yeah, just the image cutouts, that's right.
Okay. And so based on just the GRI cutouts, you're getting all of this information regarding the spectral lines and so forth with the BPT diagram. So one question that I have is, have you considered like expanding this to cover more filters? Like, for example, hypersuprime cam has all the way from G to Y band. We have DPU band imaging, even medium bands as well to get better constraints on emission lines contribution as well. Like including that, will that really help with the in a sense, outputs that come out of this in terms of like modeling or recovering spectra or predicting the spectra?
Yeah, it's a great question. I mean, there's always a trade-off, right? Because generally, if you look at just the intersection of different, parts of your survey or whatever, for example, including narrowband, it will help, but it'll reduce your sample size. And so there's an interesting trade-off that's at play there. It's the same way that if you had to design, the high latitude wide area imaging survey or something, like you've got to make trade-offs. Like, do you want to go deeper? In this case, do you want to use all the bands? And I think that like those are the kinds of things that we have to consider. But of course, you're right. There is more information there, and there's actually really interesting stuff, right? Like you've got you might, especially with like with narrowband filters and things like that, you might be able to hone in on like interesting features that otherwise are invisible or drowned out. And so I think that there's potential for that. I'd love to chat more if you have very specific ideas, using HSC survey or whatever else.
Yeah, I was just considering because we have all like, this immense amount of imaging data in so many, extragalactic legacy fields. And We're going to get a
Yeah.
lot more and much wider field. So I was considering like how we could incorporate that information to even refine predictions. But the thing that kind of I still am having a hard time grasping. I think Swara also talked a little bit about this and a couple of other people too. When it comes to the emission line predictions, I mean, you have three filters, GRI, they're wide filters, and you're showing us like O3 divided by H beta, N2 divided by H alpha. I mean, N2 H alpha will fall in one band, O3 H beta will fall in another band. And the question I have is how like reliably are those like ratios really being measured? I mean, is it just because you're pre-training it on spectra for galaxies that also have these morphology cutouts that it knows to expect that, okay, if the galaxy looks like this, we should expect an O for H beta ratio and to H alpha ratio like that then? Is that what's happening?
Yeah,
But
I
you're
mean,
not resolving the line itself into images.
no, yeah, by no means are you doing that. And in fact, you can make this learn things that are well outside of the film. Like we can learn the H21 centimeter, flux, which obviously is not in an optical line. And the reason is because, and I think this is the essence of it, is that